So let's look at the best and the worst case complexity of the nested loop approach that we just saw, the naive approach for solving the pair sum problem. Well, the best case is the lucky scenario where it turns out that the very first pair that we try happens to beat the target. It's like exactly like linear search. The very first item I find happens to be the item of interest. Then in that case, I just do it in, let's say, one iteration. But that's just like a pathological somewhat. More interesting is the worst case. Well, the worst case in linear search is basically none of the items is the item that I was looking for. In the same way, in this case, the worst case is none of the pairs adds up to the number that we had as target. So, like I said, in linear search, basically number not in the list. Same idea that none of the pairs adds up to the target. Let's see how many comparisons are needed to do in the worst case. In fact, this diagram gives us a great hint. We have the length of the list as 1, 2, 3, 4, 5, 6, 7, 8. And, with 20, I'm going to form 7 pairs and then 6 pairs, then, 5 pairs, 4 pairs, and so on and so forth. Is that for a list of length n, I'm going to create 1 plus 2 plus 3 plus, all the way until n minus 1 pairs, which is given by n times n minus 1 by 2. So, this is a formula that we learned. In fact, something like this we have seen before in the platformer game when we computed how high the sprite is going to jump, right? So if I look at n times n minus 1 by 2, that's n squared by 2, that's from here, minus n by 2, which is, well, approximately equal to n squared by 2. So the important point here is this is not exactly equal, but it's approximately equal. And as we make n large, you find that n squared by 2 is in fact much, much, much larger than n by 2. And the error that you're making by ignoring this n by 2 is in fact minuscule. So for example, if I were to take, let's say, n of 1000, the n times n minus 2, the exact number is 4995000. But if I were to ignore the n minus 2, I'm just making a 0.1% error, which is minuscule. And you can imagine that as n becomes larger, say a million, this error will become even smaller. So the point to understand is that, look, this is n squared by 2 operations, but even more important, from the perspective of, let's say, complexity analysis, the important conclusion we are going to make is that, look, the number of comparisons in this search is increasing as a function of n square. Now, this is the, let's say, the nature of the nested loop, because remember there are two loops. So first, there's an outer loop, the inner loop. And you can think that for every item, I'm effectively pairing it up with the entire list one by one, and hence the complexity has to be of the nature of n square, right? So compare this to linear search. The number of comparisons was a function of n. N square, in fact, scales much, much faster than n. And we'll see this in just a moment. So basically, now in order to understand or appreciate the impact of this quadratic scaling, let's say I go and import, time. And then I create, let's say, a number. So maybe start with, say, maybe 10. That's all right. Um, I define a number n, which is going to be the length of my list. Let's say I start with 100. Now I create a list L, which is, a list computed by positive numbers, say range n. So, notice this is a list with numbers 0, 1, 2, 3, 4, 5, 6 until n minus 1. Let's say I set my target. So I put IDX to be, say, pair sum, L, this list that I just created, and a negative number. Notice the numbers in L are non-negative, which means 0 and until n minus 1, which means that there cannot be a pair that adds up to a negative 100, which means we are really pushing the worst case here. And we will see how long it takes to do this. So as before, I'm going to say T naught is, say, time dot time. And once the function runs, I'm going to say T1 is equal to time dot time. Now I know it's going to return minus 1, but so I will just say print T1 minus T naught. And this is something we've done before. This gives insight, right? So if I start doing this now, you notice when I run this for 100 times, it's 0.0005. It's quite minuscule. In fact, so in that order, let's say I go to, so notice there are 3 zeros here, and then I see a number, right? So that order here, if I go to 1000, in fact, this is now 0.03, right? So, significant increase. When I go, let's say, to 10,000, notice I'm increasing the input by 10. And this is starting to take really, really long, right? So 0.0, let's say, 3 or something like that has now become 3.7. If I were to go one more zero, now this is really going to take long. In fact, it's going to take a few minutes because this is quadratic scaling. the running time is going to increase as the square of the input. When I increase the input by 10 times, the running time in fact becomes 100 times, which means if I was running for around, let's say, 3.7 seconds earlier, now we are looking at something like 370 seconds, which is in fact 6 minutes, right? So while this runs, let me just show you the last time that I run this. Now, the exact runtime numbers may be different when you do it, but the point is very clear. You notice that as I increase my n from 0, say 1000 to 10,000 to say 100,000, which means a factor of 10 increase, in fact, the running time is increasing approximately by a factor of 100. And that is the nature of quadratic scaling. Really, really going to be very heavy if I were to increase this further. All right, so waited and waited till it got over, and it's already 403 seconds. So we see that 3.7 seconds or something like that has become 400 seconds, which is quadratic scaling in action, right? We'll see that for a sorted list, we can bring the complexity down by using the two-pointer technique. But I hope this was interesting. Looking at these runtime numbers really gives us a feel for what does this scaling really mean. As always, do look at our website www.ybyte.in and forever enjoy coding. Take care. Thank you so much. Bye bye.